Welcome. In this video, we're going to determine whether this integral here, this improper integral that is, whether it is divergent or convergent for values of p that are less than 1. So let's begin with a number line. And here's the number 1 right here on our number line. So we want values of p that go from 1 down in this direction. And now you might be wondering, why did I just sketch a basic number line in a calculus course? Well, this is going to help us figure out some cases. We would all agree that 0 lies to the left of 1 on a number line. And 0 is going to be one of our cases. Another case is going to be from 0 to 1. And then another case is going to be for values less than 0. So let's go ahead and number these 1, 2, 3. Let's begin with case 1. So in this case, p lies inside the interval from negative infinity to 0. And if you've never seen this little backwards e symbol before, this just means inside or in. Like I am in my house right now. I could put person in house. That would be person in house, just like this is p is in this interval. So since p is in this interval, we can say p is negative. So p has to equal negative d for some positive d. So now let's integrate 1 to infinity of 1 over x to the p dx is equal to the limit as t approaches infinity of the integral from 1 to t of 1 over x to the negative d dx. So as you can see here, I just replaced this exponent of p with a negative d. Well, let's rewrite this further. This is the limit as t approaches infinity of the integral from 1 to t of x to the d power dx. This evaluates, and of course we're leaving the limit up front, to x to the d plus 1 power divided by d plus 1 evaluated from 1 to t. Now this d plus 1 in the denominator, that's just a constant. So if d was 3, then that would be a 4. So I'm just going to go ahead and factor that out to the front. So I have 1 over d plus 1. And this is times the limit as t approaches infinity of t to the d plus 1 minus, and now I could put 1 to the d plus 1 power, but 1 to any power is just going to be 1. So I'll just say minus 1. Now what does this look like? Well, if d plus 1 is even, then the graph of t to the d plus 1 power minus 1, and to save myself from having to write this over and over, I'm going to call this g of t. So this entire quantity in the limit, I'm going to call g of t. Well, if d plus 1 even, the graph of g of t looks like this, and this is of course our t-axis, and here is negative 1. Now if d plus 1 is odd, then our graph is going to look like this. And here again we have negative 1. So either way, whether d plus 1 is even as we have here, or d plus 1 is odd, either way, as t approaches infinity, g of t is going to also approach infinity. That tells me that this limit here equals infinity. So this constant's going to make no bearing. What happens if we multiply a unit fraction by some larger and larger number? Well, the unit fraction is going to have no effect. So to reiterate, this limit just evaluates to infinity. Since we do not have a finite value here, for this case, when p is some negative value that is on this part of our number line, so from 0 off to the left, then this integral is divergent. Okay, so now let's take a look at our second case. So our case 2, and that's the case where p is equal to 0. So our integral from 1 to infinity of 1 over x to the p dx can be rewritten as the limit as t approaches infinity of 1 to t, of the integral from 1 to t, that is, of 1 over x to the 0 dx. Any value to the 0 power is just going to be 1. So this is the limit as t approaches infinity of the integral from 1 to t of just dx. This evaluates to just x. And of course our limit stays in front. So this is x from 1 to t. So we're evaluating the limit as t approaches infinity of t minus 1. Now as t gets larger and larger, say t is 3, then the limit will be 2. If t is equal to 10, then this limit is going to equal 9. If t is equal to 1,000,001, then this limit is equal to just 1,000,000. Can you see what's happening here? As t approaches infinity, t minus 1 is also approaching infinity. So this limit here is equal to infinity. That tells us if p is equal to 0, then this integral from 1 to infinity of 1 over x to the p dx is divergent. And let's go ahead and write that down here under our case. Okay, so we figured out case 1 is divergent, case 2 is divergent. Let's see what happens in case 3. Okay, so now we're in case 3. That is p is between 0 and 1. So that is 0 is less than p is less than 1. So we can think of p as some fraction. So p equals some a over b, where a over b is between 0 and 1. And we don't actually need to rewrite p. I'm just doing this to really illustrate the next point, that is x is always larger than x to some fractional exponent. I feel that writing this as a over b makes it easier to see that p is indeed just some fractional exponent. This tells us that 1 over x is actually less than 1 over x to this fractional exponent, which is just 1 over x to the p. Furthermore, we know that this is always going to be larger than 0 since our x values are running from 1 to infinity. So we've established that 0 is less than 1 over x is less than 1 over x to the p value. And now we're going to evaluate the integral from 1 to infinity of 1 over x dx. So let's rewrite this. This is the limit as t approaches infinity of 1 over t. That is the integral from 1 to t of 1 over x dx. This is the limit as t approaches infinity of the integral of 1 over x evaluated from 1 to t dx. Integrating yields the natural log of x evaluated from 1 to t. This is the limit as t approaches infinity of the natural log of t minus the natural log of 1. The natural log of 1 is just 0, so this is the limit as t approaches infinity of the natural log of t, which is infinity. Wonderful. Now, because this inequality holds, and this integral here diverges, we know by the comparison test that our original integral has to diverge. That tells me that 1 over x to the p on this interval between 0 and 1, that is our case 3, is also divergent. Well, to summarize now, we looked at 3 cases, 3 possible options for the value of p, values of p that are negative, that is less than 0, the one value, the one time that p will equal 0, and then values of p that are between 0 and 1, that is, they're fractions. And in each of these cases, we notice that this integral is divergent. So let's write that down. The integral from 1 to infinity of 1 over x to the p dx is divergent for values of p less than 1. I hope this video was helpful.